Okay, hello everyone. Today I'll be presenting Lumiere, a space-time diffusion model for video generation, recent SIGGRAPH Asia 2024 paper by Google Research. The paper introduces a new architecture for generating high-quality, coherent video using diffusion models. And I'll walk through the motivation, the challenges, the system, and maybe some of my feedback on it. So, this is my context and what I'll go through. So, let's talk about the introduction. This paper proposes Lumiere, a diffusion-based model designed to generate a full video sequence, 80 frames over 5 seconds in a single pass. So, why is this important? Well, video generation today faces fundamental limitation. Existing approaches typically generate keyframes and then rely on temporal super resolution to fill the missing frames. This two-step or even three-step pipeline often results in noticeable artifacts, flickering, temporal inconsistency, texture shift, motions that feels unnatural. So Lumiere is motivated by the need to avoid this cascading pipeline entirely, and instead create a model that can see the entire video at once and generate it holistically. This leads to much better motion consistency and texture coherence, stability, which is what an artist, animators, or even content creators will really want when they try to create controllable video output. Now, even though Lumiere is not a traditional computer graphics algorithm, there are no rasterizers, no ray tracing, no explicit BRDFs, it actually behaves like a machine learned inverse approximation of the entire CG pipeline. When we look at the results, we can see it implicitly, learning concepts we studied in this course, such as shading, lighting, texture coherence, occlusion or visibility, or even perspective projection. It has no geometry or rendering equation, but it learns the appearance of all those phenomena through data. So this paper sits at a very interesting intersection between CG and generative AI. Okay, so let's talk about the problems and challenges. The central problem addressed in this paper is how to generate a full coherent video directly. So instead of assembling it piece by piece, prior systems break the video into steps like first generate sparse frames, then run the temporal super resolution to interpolate. While this pipeline is easier for computational, it creates a disconnect. Each stage has its own assumptions and errors that will be accumulated along the way. Now, there are several important challenges that make end-to-end video generation very hard. First, long-range temporal modeling. Motion in video often spans multiple seconds, and actions like dancing, camera pans, or objects interacting require the model to understand the entire sequence, not just a short video window of 4 to 8 frames. Texture. Second, texture and appearance stability. Textures must remain attached to surfaces. This is similar to what we learned about UV mapping and avoid texture swimming. However, diffusion models do not explicitly track UVs. They must learn texture stability implicitly from data. Now, third is memory and compute limitations. Storing the latent representation of 80 video frames and generating them through a UNet is extremely memory heavy. Now, the fourth is training instability. The temporal gradients are noisy, so as we increase the sequence length, gradients may explode or even vanish. And then the fifth one, versatility. The goal is not just to text to video, but also image to video animation. Stylized video generation and painting and other editing tasks all using the same model. These challenges make the problem much more complex than image generation, and solving them meaningfully is what Lumiere aims for. Now let's talk about the question for this. So how can we generate a complete video sequence directly without relying on keyframe hierarchies or temporal super resolution? And this is what this paper wants to compete. So the intuition behind Lumiere. The intuition behind Lumiere is actually quite elegant. Instead of thinking of video as a sequence of frames, Lumiere treats it as a spatio-temporal 3D volume. Uh, Imagine a video cube where the axes are height, width, and time. So if you adopt this perspective, then the natural thing to do is to extend the 2D UNet architecture into 3D. So that it can downsample and upsample not only spatially but also temporally. This is what the paper calls the space-time UNet. So the key intuition is If the model sees the whole spatial temporal volume at once, it can ensure that the motion is globally coherent. This means that the model learns how objects move, how the texture patterns stay fixed, and how motion floats across the full video. So after generating a low resolution coherent video, the next step is to increase the spatial resolution. So instead of temporal super resolution, Lumiere uses only spatial super resolution, applied on overlapping windows. So multi-diffusion blends these overlapping windows smoothly, preventing any seams or inconsistent patches. So the main idea: generate a globally coherent video at low resolution, and then use overlapping spatial super resolution windows to upscale it cleanly, and then avoid any temporal interpolation that breaks motion. Okay, and then I will talk about the overview. So the overview. At a high level, the Lumiere system follows a straightforward pipeline. First, the user provides a text prompt, an image or an input image or an existing video. The system encodes this into a latent representation using the space-time unit. Lumiere generates a low-resolution video, but crucially, it generates all frames at once, ensuring the consistency. After this, Lumiere applies spatial super resolution. What makes Lumiere impressive is its versatility. It supports the text to video, image to video, stylized video, video in painting, and cinema graphs. Because all these tasks use the same learned model, Lumiere function more like a unified video generative platform rather than just a single purpose model. So next one, we'll talk about the implementation. First one, we talk about the space-time unit. The space-time unit extends 2D convolutions to 3D. That means the model can perform downsampling and upsampling not just across spatial axes, but also across the temporal axis. This gives the model several advantages. It reduces the computational load by compressing the temporal dimensions during inference. It allows the long-range temporal dependencies to be captured at lower resolution and avoids the short temporal window problem found in other models. Now, the super resolution stage is also critical. Instead of temporal super resolution, which often causes flicker, Lumiere uses only spatial SSR. This one. And then and it does it with the overlapping windows. So multi-diffusion handles the blending of these windows because the windows overlapped. They produce smooth transitions and stable textures. This combination, global temporal modeling plus overlapping spatial SSR, is what gives Lumiere its advantage in temporal stability. And then next, I will talk about their implementation. Implementation details. This model uses a 3D inflated unit architecture, similar to those used in video segmentation or action recognition, but adapted for diffusion. The latent temporal resolution is reduced significantly so that the model can fit in the GPU memory. So even though the model is complex, it supports many applications seamlessly. So image to video generation is particularly impressive. Lumiere preserves facial identity, clothing textures, stylistic details very consistently. So stylization, video stylization allows the applying an artistic style to the entire video without frame by frame inconsistency. And then for in painting can fill missing regions and produce coherent motion. Cinema graphs allow the parts of the video to remain still while others are animated. So this versatility is one of Lumiere's strengths. Now I'll talk about the generation pipeline. The slides show the flow visually. The pipeline starts with encoding the prompt or image. The model generates a low resolution video containing all the temporal information. Then spatial super resolution applied through multi-diffusion windows enhances details. Finally, the windows are fused into a single output video. This multi-step approach ensures stable textures, details, and consistent motion without the need for temporal interpolation that usually causes artifacts. And then next, we will talk about qualitative evaluation. In qualitative comparisons with existing models, Lumiere clearly excels in temporal stability. Previous models often produce like flicker, shape distortions, or textures that drift between frames. Lumiere maintains stable textures, consistent character identity, and smooth camera motions. For stylization, the model applies a consistent style across all frames, avoiding the style jitter that plagues other diffusion-based stylizers. In painting tasks, Lumiere fills a missing area while preserving consistent motion cues. Human evaluators preferred Lumiere's output over other baselines in almost all categories, from the temporal coherence, the visual quality, the stylistic consistency, and the overall appeal. So let me talk about next the strength and weaknesses of Lumiere. So the strength includes best-in-class temporal consistency among diffusion models, unified architecture, no multi-stage TSR, stable textures that attach correctly to objects, preserve identity to image to video task, and versatility. One model handles several video tasks. However, the paper also shows several weaknesses. Model can be overly smooth or simplistic, especially when physics is involved. Complex interaction or crowds still confuse the model. The model only generates like a 5-second clips, which is limiting, I think. And then no explicit 3D geometry, leading to subtle distortion in occlusion and perspective. Camera motion is not explicitly controllable, it's mostly learned implicitly. So these weaknesses point to the limitations of treating video purely as an appearance-based problem. Now, conclusion the conclusion, to summarize it, Lumiere demonstrates that generating entire videos in a single pass is a powerful strategy for improving temporal consistency. The spacetime unit and the multi-diffusion based SSR together provide a clean, unified pipeline that outperforms previous multi-stage methods. To compare to related work like Penaki, which is Penaki can generate like longer videos but with very low visual quality, and then another one is Imagine Video and Video Poet produces good frames but suffer from flickering because of the reliance on TSR. And then Pika and Runway models generate strong short clips but only within a restricted temporal window. So while Lumiere represents an elegant engineering solution, it does not fundamentally solve the problems of physical correctness or 3D structural consistency, because it learns purely from appearance and not from the geometry side. It sometimes makes mistakes that a physical-based renderer would never make, like inconsistent shadows, warped limbs, or unnatural camera motions. Furthermore, the 5-second maximum length limits the creative usage. A truly general video generation system would need to handle much longer sequences with explicit control over camera paths, object trajectories, and physical interactions. So I view Lumiere as an important step forward, but not really the final solution to video synthesis. Last but not least, the limitations and contributions. The key limitations is like first, I talked just now, it only generates a 5-second clip. No physics, no real 3D structure, and it cannot guarantee correct occlusions or lighting. And then it is computational expensive output, and it's not deterministic. But the contributions are significant. It introduced the first practical space-time diffusion architecture, the space-time unit. It demonstrates full sequence generative modeling and shows superior motion consistency without TSR. And then next, it provides multitask support within one unified framework, and it pushes the field towards global spatial temporal modeling. So overall, Lumiere is a strong and influential step in the evolution of video diffusion models, and that's all for me today.